All right, good morning, everybody. Oh, who do we got in now? Alex is here, excellent. All right, I'm sure the others will be along shortly. Speak of the devil, as soon as I say it. All right, but we got to pick a start time somewhere, right? Kaylin and Ruby. Oh, the whole gang's here. Even better. All right, so that's up and running. Everything is working. Fantastic. We've got a wonderful day today. We're going to take all of the things we've been working on, all of the analysis from our rational functions, all the asymptotes here and holes over there, and we're going to stick them all together and finally start graphing these suckers, okay? And this is perhaps one of the most satisfying things I know of in algebra land, as it were, just because it looks so darn impressive. Honestly, like, yes, we have calculators that can do it for us. We have computers now, okay? Graphing is not that big of a deal. Do you need to be able to graph this thing by hand? No, okay? You're not gonna have a calculus class where you don't have a graphing calculator available. That being said, it's a really good skill to be able to quickly create a picture in your head. Okay, now since you're still in school and I have to analyze whether you know what you're doing, you have to transfer what's in your head onto paper so that I can see it, right? So in that sense, you have to at least be able to put it down on the page. But really, the heart of what we're getting at is to be able to create a picture in your mind so that you see this equation, you know, in the middle of your big calculus problem. You can say, oh, well, let's say, oh, that's going to have an asymptote right here. Okay, keep that in mind, right? And those kinds of things so that you know what it looks like and you can check your work as you go. Does this make sense? Okay, if I find the derivative here and then it's, wait, that shouldn't be negative because it had the whole that, right? These kinds of things, that's ultimately what we're aiming for. But along the way, we get to have, in my opinion, a lot of fun with these. Because it was not that long ago that people thought graphing these by hand was nigh impossible, okay? My high school teacher used to tell me a tale of how she went to some kind of conference. It was a teacher's conference or something. And they were talking about how to teach rational functions, and the presenter brought up the fact that, well, you can't really graph these by hand, you have to use the calculator. And she raised her hand and was like, wait, no, I can graph that. There, it's got an asymptote here and a hole there and a slant asymptote of this, and boom, done. And they're like, what? How do you do this? And so it still mystifies a lot of people. So you can show off to your friends with these skills right here and just whip up quick sketches of these things. So I'm going to run through 1, 2, and 3 for you today in class, so you've got a good sampling of examples to see. Your mission will be to finish off the rest of these and create the graphs for them and turn that in by the end of the day. Okay? We should already have most of the information. I'm still writing on the same page here, but we did the intercepts. We did the, we also included the excluded values here. We have the asymptotes, we have the holes, so we should have that whole list, right? So for number 1, let's see, the first thing I would be doing with this is I would factor it out and I would check for holes. Since you guys already did this, can you tell me in chat where, if any, are the holes on function 1? Alex and Gabriel say none. There are no holes. I can immediately see that must be correct. And I know that because the top doesn't have any factors. There's no values of x that cause the numerator to be 0 because the numerator is a constant. In fact, because of that, I know there should also be how many zeros of this function? None, right? There's no values of x that will cause the whole function to equal 0 because you can't make the numerator equal to 0, right? So this thing will never cross the x-axis. Okay, don't let that freak you out. Remember, the most basic of rational functions is, why did I put dots, is 1 over x. It looks like, I give a little more curve to it. It looks like that guy. Never crosses the x-axis. Okay, so everything we're doing today is an expansion of that. All right, so the only thing left then is asymptotes. Right? So then how about horizontally? Are we dealing with a horizontal or a slant here? Or no horizontal or slant? What's the, who wins the power war here? We've got a power of 0, the numerator, 2 in the denominator. So denominator clearly wins, right? Bottom wins, yep, Alex has got it. So that means we're going to have a horizontal asymptote at y equals 0. When x gets really, really ridiculously big, put in several million for x. We're going to end up with a million squared on the bottom. 4 divided by several millions is basically nothing. Okay, if you were given 4 millionths of a pie, you would be really disappointed with that slice, right? That's my measure. That's like my go-to fractions. Like, okay, how much pie would that be? Would I be happy with that? No. Then it's not a. Of course, okay, maybe that's a bit carried away because I wouldn't be happy with like a 16th of a pie. That's also kind of small. Anyways, we've got a horizontal at y equals 0. How about verticals? Are there any values of x that make the denominator equal to 0? Right, 2 and -5. Yeah, okay, so we'll say x equals -5, x equals 2. I'm just going to list them out as individual equations right here. So this is the actual equation of each of my asymptotes. Since I've already done the work. When I say I mean you, right? But this gives me a good collection. This is like the final list of things to actually put on the graph. So let's go ahead and draw this guy. I need a set of axes. I'm not seeing anything that says make it imbalanced, right? There's no reason not to center it around the origin. I've got an asymptote on either side, a positive one and a negative one. And they're fairly close-ish together. So let's look at that. Let's start with those asymptotes. We'll go x equals, not too much, 1, 2. And 1, 2, 3, 4, 5 out here. Let's make my negative x-axis a little bit longer to accommodate. There we go. Now I've got 1, 2, 3, 4, 5, all 6 regions. The one thing I was missing, what about, we said there's no x-intercepts. What about y-intercept? If I do put in when x equals 0, what do we end up with? Because that'll dictate to me where this center portion goes. Does it go up in the top or in the bottom? So mostly I'm looking for the sign of that number. We can get a specific value here. No reason not to mark that on our graph if we have it. Nobody's telling me what it is though. Guys, plug in 0 for x. What did you get? This goes away, that's 0. That's 0. All that's left is this guy here. That's in the denominator, yeah, but the whole thing then becomes the function still has that 4 up top. Okay, technically -4/10 would also work. Reduce your fractions, folks. 4/10, they're both, what happened? Why'd everything go blank? Somehow I managed to zip to the end. Okay. Couldn't do that again if I tried. All right, y-intercept of, -2/5. So negative of, not a whole lot, but it is down there. Okay, we know it's down there. We know we've got horizontal asymptote, which we will get close to when we have nothing else nearby. Okay, and particularly on the ends. Right? You are allowed to cross the horizontal asymptote if it's not on the x-axis. You can cross it anywhere as necessary. If it is the x-axis, you obviously can only cross the x-axis at specified zeros. So since they are one and the same, our horizontal is the x-asymptote, I'm not allowed to cross it anywhere because we have no zeros. So this guy has to fit into here, and he's just going to curl down like this, and then I'm done with that middle region. And as I said, we're usually flipping top and bottom when you switch from one region to the other. And I can double check that by checking the sign when x is very large and very small. Okay? If I put in a several million for x here, it's going to square. A million squared is still positive millions. Okay? The rest of this is barely a trifle. So this stays as a positive number. So I should be on the positive side of my horizontal asymptote here. And if x was negative million, well, negative million times -1 million, the squaring effect causes it to be positive again, and so I stay on the positive side over here. Not exactly every time. That's usually the case. Most of the time you will flip. Yes. That is the general rule for an asymptote, right? Is that the function is trying to go along, it's trying to travel horizontally as best it can. It wants to just go, but it runs into this wall and it goes, nope. And then it comes back again, looping from the other side, right? Again, remember your parent function, right? 1 over x. Vertical asymptote at 0, and it flips. But 1 over x squared, right? My asymptote is like a double root, right? Similar to how we had double roots with polynomials, we could have double asymptotes, and that's when you get the same side. Okay? But that's more of a general pattern. I would say the hard and fast rule is plug in 1 million for x, plug in -1 million for x, see what sign you would end up with. Okay? Right. Yeah, we know this one has to go down in both sides to it because I'm not allowed to cross here because I have no zeros. So this is really kind of a thinking puzzle now, right? And that's why I think these are kind of fun. Is that once you've done all the algebra work, now you're into puzzle mode. And okay, how can I fit these pieces together such that they make sense? And you get okay. How'd you get the -2/5? Okay, plug in 0 for x. This becomes 0, this becomes 0, this becomes 4 over -10, reduce that fraction. Excellent. All right, final questions on function 1. All right, then let's go to function number 2. What do we know about function 2? Let's switch colors here. No, I'll do red this time. We'll save purple for 3. Okay, first up, if you factor numerator, denominator, check for common roots. Does function 2 have any holes? And I think I even have some work up here. Where is it? Aha! Here's my prior work on function 2. We've got the y-intercept 2, hole here at 5/2, no vertical asymptotes, and a 0 at -2. So hole at, yeah, we'll write that as x equals 5/2. I did zeros next, so we'll keep that in the same order. Zeros was it -2? Sorry for all the zipping around. Asymptotes, vertical was none, right? Because the only vertical we had left, the only excluded value was that 5/2, which became a hole. So we have no vertical asymptotes. That's kind of nice. But we do end up with a slant asymptote. Right? Comparing the powers here, numerator wins, x squared versus x, and it wins by exactly 1. So in the end, and by the end I mean when x is very, very big, in the millions, it's going to look like a linear function. It's just a straight line. Slant asymptote at the ratio of those two gives us just 2 minus 10. So we have y equals, not negative x, just x, minus 10. There's the negative. Okay, and last thing, the y-intercept. If x is 0, this becomes 0, 0, -10, 0 divided by -5, and you get 2. Okay, any dispute on that information? Are we good there? Okay, then let's construct some axes. I don't have any vertical asymptotes to worry about. I do want to make sure I'm covering these x values within, so let's make sure we mark off enough space that we can see where those will be. So the -2 here, and 5/2, 5 divided by 2 is 2.5. So let's put a tick out all the way to 3. I can see where 2.5 will be. And the vertical, we want y-intercept of 2. So we will have a point there on our graph. Our slant asymptote is the only dashed line to draw in. Go back to orange for that. And that's just a straight x, but -10, way down here. So it's going to come something like, oh, not even like that, actually. It's going to end up way out, crossing like way out here. Maybe I just need to zoom out even further for this one. The x-intercept of such a line, right? You'd have to have x equal to 10 for that to cross. So it's going to cross way out there. So we're not even going to get to see that at the end there. But I'm allowed to cross at -2. So let's see, what can we draw here? Something that goes through here, crosses at -2, right? But eventually comes down to approach the asymptote. And this cross also has to approach the asymptote. So really, is it that much of a, why is it -10? I don't think it's supposed to be -10. I think I may have messed that up. This looks really awkward. It should look mostly like a straight line except for that hole. Let's check. When in doubt, use your graphing resource. Say, hey, I think I've screwed something up here. What should that look like? Let's ask Desmos, huh? Which is, I've got installed one here somewhere. And let me pull up the actual function so I can type it in. Here we go. We need 2x squared minus x minus 10. I need the whole thing divided by. So let's stick that in some parentheses. There we go. 2x minus 5. Aha! Look at that guy. So what did we do wrong here? Because this is just a straight line. It goes through our y-intercept, it goes through our 0, and it probably has that hole around somewhere, 2.5, right? Oop, see that? I lost it. Hold on. 2.5 comma undefined. Desmos does a really bad job of actually marking the holes for you unless you hold on to them, so you cannot rely on that. Let's go back to our graph. Why should the asymptote be at, also have a y-intercept of 2? Turns out you need the constants of both of these. So I think I must have misspoke earlier when I was first describing it. It is the ratio of the lead coefficients and the constants. You're going to need both of them, not just the constant of the numerator, the denominator as well. Right? You want that final reduced effect when you factor everything out, which does make this much easier to draw. We have our 0, we have our y-intercept. We want basically a straight line running through those, except for right here where we have a hole. And that'll be at 2.5. Okay, any questions there? Again, slant asymptotes are probably the trickiest to deal with. Luckily, they're not that common. All right, then let's go on to number 3, final round. What do we know? Do we have any holes to worry about? So I think I had some work on number 3 earlier. Yeah, there we go. Okay, so based on just that, do we have any holes? Oh, now you ask Ruby. I called earlier. Okay, I'll come back to it. Give me a moment. Holes on number 3. Look here, my possible zeros versus my possible asymptotes. The common value is 4. So we're going to have a hole at 4, 0 at -3, an asymptote at 0. So hole at 4, 0 at -3, asymptote at 0. Okay, back to question 2. Sorry to flip on you. We had some question about the asymptote here. Why is it x plus 2? You're looking at comparison of exponents. Numerator wins by 1. I know it's a slant. Therefore, I need the ratio of these guys and the ratio of those guys. I still need both my constants, okay? Because the y-intercept of your asymptote will still represent the y-intercept of the whole function. Okay? Y-intercept is always what happens when x becomes 0. That shouldn't change. Okay? It doesn't mean, well, yes, it does. Your asymptote will go through there, but it doesn't always line up, right? Like we had the asymptote here, the horizontal at y equals 0, but the actual y-intercept of the function is separate. Okay? They're only going to match up when it is the slant asymptote. Or you get 0 is also your 0. Right? 0 is just this such a unique thing. You always get, it's very hard to draw general rules. Because 0 is always the number that's the exception to all the rules, right? Could have zeros everywhere. Yeah, slant asymptote's going to be, because you think about reducing this. Only the highest powers matter. So I basically cross out the extra x's and I just divide 2x squared divided by 2x. I'm left with 1x. So that's why I get this. My y-intercept is still, if I make that whole thing equal to 0, it's still going to be ratio of the constants. So that does hold out. All right. This guy, however, is much easier. Back to function 3. Compare these powers. It's a tie, 2 to 2. So when x gets really, really big, we have 1,000,000 squared divided by 1,000,000 squared, which is just 1. Right? So when it's a tie, it's a horizontal at the ratio of their coefficients, which are currently invisible 1s, so it's just a 1. So y equals 1. That's my horizontal asymptote. And our y-intercept, plug in 0 for x everywhere, you get negative, no, not 2, 12. So let's whip up a graph for this guy. Get a set of axes here. I didn't mean for that to be a curve. Okay. Positive, negative, positive, positive, some very negative. Okay, I want to make sure this goes all the way down to negative 12. So let's go by 2s, at least on the y-axis. 2, 4, 6, 8, 10, 12. Okay, call that negative 12. On the x-axis, I don't have to scale the same. So we'll just go 1, 2, 3, 4, 1, 2, 3, 4. And draw in asymptotes at x equals 0. What? Wait, so I don't have a y-intercept. If there's an asymptote there, I can't cross the y-axis. Okay, it would like to think that it's a negative 12, but nope. You get no y-intercept. Just kidding. Erase that. Well, I guess it doesn't matter how I scale my y-axis now, does it? Okay, keep going. Asymptote there. Horizontal at y equals 1, so we'll go, here's y equals 1. Get rid of that scaling. I don't need that anymore. 1, 2, 1, 2. Good enough. Okay, got my dotted line in. And we do have a 0 at negative 3. So draw that in. 1, 2, 3 right there. Now I know I cross there, which guarantees that this region, the function is in the lower half. Okay, so we draw in something like that. And then the other side will, of course, naturally flip, I believe. Double check there's any reason for it not to flip. Is this like a double root of 0? No, but we do have that whole at 4, right? Again, when x is positive million, that's positive, the sign stays positive, right? So we just got to draw in our whole at 1, 2, 3, 4, so right there, down to 4. Up a little bit. All right, final questions on function 3. And I think that's how most of them are going to go. I don't believe any of these functions had more than 2 vertical asymptotes. Right, nothing even, yeah, I don't even see a cube power up here. Right, squared, 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 squared. Yeah, so you really can't even have more than 2 asymptotes on any of these. So not too shabby. All right. Okay, you've still got about like 12 more minutes to work, so go ahead and get started on sketching up the rest of them. Okay. Again, this kind of sketch is perfectly adequate. If you really wanted to pretty things up, right, make sure you've got your arrows on everything, the axes and the actual function line. I don't think that asymptotes really need the arrow tips on the end, but you can probably label your axes and throw down at least one number here. I like using 2 just because 1 looks like a vertical line. If you just do that, I don't know if that's a stray mark. All right, so just so I get an idea of how you've scaled your axes, if it's anything other than 1, this is absolutely required. If every tick mark represents 1, you can get away with leaving that off. We'll know what you mean. But that would be like the most complete graph, right? If you have all that, you're set. You got everything you need. Okay. All right, I'm not getting any final questions here, so I will leave the rest to you. Have at it.